We are ASU ROAR, the robotics team of Ain Shams University. I am Abdurrahman and I have the honor of leading this team. Driven by passion, shaped by challenge, and united by one goal, to leave a mark on every stage we step on. We have competed on international stages, Formula Student UK, Shell Eco Marathon, and Formula AI. Every competition a lesson, every failure a step forward, every build is a statement. That experience lives in everything we do today, the way we think, the way we design, and the way we refuse to settle. Robotics is not just our next step, it's where everything we have learned comes together. We build, we test, we improve, we push further because we strive for success. We are ASU ROAR and we're just getting started. The ASU ROAR team operates through 7 specialized sub-teams. High Board handles strategic planning, budgeting, and external partnerships. Mechanical manages structural design and chassis validation. Robotics develops the manipulator arm and end effectors. Electrical covers power distribution, PCB design, and embedded firmware. High level integrates computer vision, sensor fusion, and path planning. Drone team handles UAV assembly, avionics, and autonomous flight software. Science conducts rock classification, pH analysis, and biosignature detection.
Participating in the European Rover Challenge is a unique opportunity for us to apply our engineering knowledge in a real-life, high-pressure environment. This pushes us beyond theory into building systems that actually work in complex scenarios. After competing last year, we were more motivated to come back, to push further and to break limits. Being one of the few teams to represent Egypt and Africa in this competition, this means a lot to us. Building on the legacy of Ain Shams University and the ASU racing team, and showcasing our potential in robotics and space exploration.
Exploration environments are unforgiving. Every obstacle, every surface, and every movement directly challenge our rover mechanical system. Our rover is engineered around a 6-way rocker bogie suspension system, enabling continuous wheel contact with harsh Marseille terrain. Stability is ensured through a differential bar mechanism integrated between both rocker assemblies, enabling controlled chassis behavior through extreme articulation. Dedicated sand and rock storage are integrated onto the platform to support efficient and reliable sample collection during ERC tasks. Overall, the rover is a unified mechanical system built for mobility, stability, and sustained performance in harsh exploration environment.
In the ERC arena, our manipulator is the rover's link to tasks, ranging from switch actuation to soil and liquid sampling. This season, we engineered our 6-degree freedom robotic arm with a lighter frame and a longer reach, giving it access to a wider workspace without compromising its stability. We refined our drivetrain with additional timing belt transmissions and chosen gear ratios to keep backlash low and motion smooth under load. A differential mechanism in the wrist provides 2 coordinated axes of motion for greater dexterity and a lighter and more compact space. Our end effector system is now fully modular with interchangeable tips tailored for specific mission needs. A new liquid sampling attachment joins our existing suite of tools, enabling quicker configuration between tasks. We continue to design and manufacture most components in-house, giving us control over tolerances and integration while pushing the limits of performance and reliability.
This season, the electrical division completely rebuilt our rover's foundation. To handle our complex system, our powertrain team designed a brand new adjustable battery pack with a smart BMS for safe, real-time power monitoring. Meanwhile, our hardware team engineered robust modular PCBs designed for the ARM and rover nodes, reducing wiring and electrical noise. We also implemented waterproof sealing and heavy-duty connectors to ensure that our electronics can survive any motion terrain.
Now with that bulletproof hardware base, the low-level software team completely transformed the rover's nervous system. We upgraded to the STM32F4 series and implemented 4-layer architecture, fully separating our hardware drivers and sensor integrations from our mission logic. We also migrated to FreeRTOS to achieve true, reliable multitasking with 0 blocking delays. Finally, we replaced our legacy canvas with micro-ROS. This gives us native ROS suit topics for seamless, real-time transmission of sensor feedback to the Jetson Xavier.
Building a robust rover starts with hardware, but intelligence is what wins the competition. Building upon last season's architecture, we have upgraded our system to ROS 2, facilitating the integration with low-level software using micro-ROS and being up to date with latest software features. But how to validate all of that? This year, we have built custom testing environment to test and benchmark each individual module and the system as a whole. For practical and reliable architecture, we have Dockerized each system module and managed them using Docker Swarm. Moving to manipulation, our 6 degrees of freedom robotic arm uses advanced trajectory planning method to maximize precision and efficiently tackle every ERC task.
For the navigation stack, our main localization approach is Visual SLAM, using the Z2I camera. In addition to a fallback strategy, Fuzzy ISKF, which fuses the raw camera data with the encoder and the IMU data. In the perception module, we implement 2 approaches. The first is a general approach using point cloud segmentation and clustering. For a lighter method, we deploy a model-based approach via YOLO and depth map. This is how we cover rocks and obstacle detection. This obstacle data is then passed to the APF local planner to ensure a safe navigation while it follows the A-star global path. To implement the planned trajectory, an adaptive pure pursuit algorithm is used. I need to highlight that this approach has been developed after proving its reliability in the last season's operation.
Our science team studies the Martian environment and we're working on understanding how the terrain evolved to be. We use aerial imagery as well as terrain models to understand geological features, and based on these, we create hypotheses and composite maps for the history of the area. Based on our analysis, we select landing sites and targets that balance between safety and scientific value. Then we plan missions for our rover that balance between distance, terrain, limits, and the quality of data to be collected. Alongside our exploration task, we're pre-calibrating our pH sensors and testing our liquid sampling tips in preparation for the ASUROAR task.
Testing our rover mobility, we controlled it remotely from the base station in all directions, forward, backward, right, left, and driving on slopes. We stop it immediately using the emergency stop button. Another showcase for the emergency stop.
This year, our drone's body is made from 3D printed PLA, but will be replaced with 3D printed carbon fiber at its final design stages. This improves the drone rigidity while minimizing the overall weight, which leads to prolonged flight duration while lowering energy consumption. In the core of the system, a Pixhawk flight controller along with an ESC is used for robust and smooth thrust control. The controller integrates data from its onboard data sensors like IMU, optical flow sensor, and time-of-flight sensor, along with sensor fusion algorithm for accurate positioning, stable hovering for controlled autonomous navigation. For the software, low-level control implements control tuning with the aid of simulation environment to improve its reliability. The communication system is designed to ensure reliable data transmission between the drone and the ground station, where it supports real-time telemetry and remote flight control. For power management, the drone uses a high-capacity battery to balance between the flight time and overall system weight.
We tested the drone's ability to perform maneuvers using wireless communication between FlySky and its receiver mounted on the drone, where the drone took off, moved along the 3 axes by controlling the thrust, roll, and pitch variables. Finally, we implemented an auto landing to land the drone safely.
This test captures our manipulator arm picking a rock sample and placing it in the rover's surface sampling storage. The 4 clips on screen show our upgraded drilling system in action, the liquid sampling system filling its sealed container in cross-section, our custom rack and pinion gripper at work, and our interchangeable gripper tips.
We are ASU ROAR from Ain Shams University, and we're excited for the chance to be part of the European Rover Challenge. We can't wait to go out there, put our work to the test, and see how far we can go.